Yes, sir. Before we continue, may I ask a question
Sure.
about this? I assume that it's just impossible to choose a gauge that is complete and do not break the Lorentz invariance.
Yeah, this is a problem. Yes, such a gauge is not possible to choose, unfortunately.
Yes, but that is why.
There is a reason why. There is a reason why. That's because if you go to representation theory, and you will ask a question about the field mu. So the field mu is a vector field. So it has 4 components. And from the point of view of Lorentz and Poincaré group, I can say that what it represents, it realizes a representation of a Poincaré group with mass squared equals to 0 equals to 0, so the massless case, and spin 1. Now, spin 1 is related to the presence of this space-time index mu. So m squared 0 and spin 1, representation of the Poincaré group. However, from mathematical point of view, this representation appears to be reducible. This representation is reducible. It means that there is an invariant subspace in this representation, but unfortunately, this is irreducible, but not indecomposable. So not decomposable. But indecomposable.
You mean not completely reducible?
Yes. Indecomposable, I mean that it's not completely reducible.
Could you please elaborate on this? I thought that since mu is a 4 vector, it is the fundamental representation of the Poincaré group. It changes by...
The point is that m squared is equal to 0. The point is that m squared is equal to 0, and in fact, the point that you have a transverse path, this decomposition in the transverse and longitudinal path, transverse path is precisely what would realize the irreducible representation. But unfortunately, in this case, I mean, you will see it in a moment. You will see it. I will try to construct this decomposition in an explicit way. You will see that extracting the transverse path from mu involves non-locality. So this is non-local procedure, which in fact is in some sense has something to do with this indecomposability, which I mean. Again, the point is the presence of this gauge symmetry. That is a thing which is responsible for this indecomposability.
Could you please remind what does it mean that m squared equals 0?
No, mass squared is equal to 0. There is no mass for this field. It's a massless field. It transforms as a massless.
Yes, I mean how it's connected with the representation.
No, all representations of the Poincaré group are divided into classes. In particular, m squared bigger than 0 and m squared is equal to 0. These are different type of representations because these different cases, m squared bigger than 0 and m squared equals to 0, in order to construct a representation theory, one needs to identify the so-called little Lorentz group. little Lorentz group represents Lorentz transformations which are left over, which keep the direction of momentum unchanged. And these transformations are different. Little Lorentz groups are different for the case of massless and the massive case. So in particular, in the massive case, as you know, massive vector field will have 3 independent polarizations. So 3 degrees of freedom. While m squared is equal to 0 is different. It will show you that in that case, only 2 degrees of freedom are left over. So massless and massive case are very, very different. In particular, in the massive case, you don't have gauge invariance. So mass breaks gauge invariance. While in the massless case, it appears this new phenomenon, this gauge invariance. And the little Lorentz group becomes different. It's not the same as for the massive case. So it's just a different series of Poincare group. You know, any representation of the Poincare group is classified by m squared and spin, or mass and spin. And those representations which correspond to m squared is equal to 0 are very different from those where m squared is bigger than 0. Well, there are also infinite dimensional representations where m squared is less than 0, so tachyons. That you can also have, but these representations are infinite dimensional and also have a different Lorentz group, little Lorentz group. So representation is reducible, but unfortunately indecomposable, which means that you are not able to detect or project on the invariant space in the Lorentz invariant way, in the Lorentz covariant way. And that's exactly related to the fact that there is no gauge which would be Lorentz covariant on the one hand, and on the other hand, complete. So either you have a Lorentz invariant gauge, but it's incomplete, or you have a complete gauge, but it's not Lorentz invariant. That is a state of affairs with electromagnetic field. But let me continue. Maybe we can say more about this decomposition on the transverse and longitudinal path. What I'm going to do now, I'm going to make this action or gauge or action for electrodynamics, or Lagrangian for electrodynamics, which we have just written down. I would like now to write it in a very clean way, stripping off the gauge degrees of freedom, show you in a very explicit way how they enter this Lagrangian. And before doing that, before doing this Helmholtz decomposition, as I mentioned, let me just note that this constraint, which we have found, it's C on X, being given by DI, it plays the role of the generator of gauge transformations with respect to the Poisson bracket. So what I mean by this is the following. So if you take C, define C, now C without X, as an integral minus 1 over C integral dx, arbitrary function chi on X, di ei on X, then integrating by parts, you can also write it as a dx di chi ei on X. Then if you compute the Poisson bracket of this generator C with AI, since the Poisson bracket between AI on X and E is canonical, then the result of this computation will be just di chi. So gauge transformation, in other words, di chi. So this means that C being applied with respect to the Poisson bracket to AI produces this gauge transformation. So constraint itself is a generator of gauge transformations. And this is a typical for first constraints of the first class. constraints of the first class, they are responsible for the gauge symmetry, in the sense that these are generators which generate the symmetries with respect to the Poisson bracket. And this is a general phenomenon. It's not only about electrodynamics, it's in general about singular dynamical systems. The statement is that constraints of the first class are responsible for the gauge symmetries. They are generators of the gauge symmetries. So wherever you have a first class constraint, it's an indication that in your theory, you have gauge degrees of freedom present. Now, what I will do, I will take.
I'm sorry.
Yeah.
Are you saying that the Gauss law is the only constraint in electrodynamics?
Yes.
Because I thought that there was at least one secondary constraint somewhere.
No, this is the only constraint which you have. It is it is preserved in time, so there is no generation of anything else. So di ei. So you have to distinguish. A constraint can be understood in two ways. Di ei is equal to 0. This is a constraint surface on which the whole dynamics takes place. But di ei itself is an element of the phase space. So it's a function on the phase space because it depends on ei. And as a function on the phase space, you can compute its Poisson bracket with any other dynamical variable. And for these other dynamical variables, it generates, as you see, for AI, simply gauge transformations. But you wanted to say something?
It's just that I had in my undergraduate studies a course of Dirac, so on Hamiltonian systems with constraints, and I remember distinctly that there were two constraints in electrodynamics.
No. Gauss law, this is only one constraint, which is dual to this Lagrangian multiply A0. And yeah, this is, I think what you might think about constraint, you think about the Coulomb gauge. Coulomb gauge is also in a way constraint, right? I think this is what you have heard probably in that case. So di ei is equal to 0. That's constraint which comes directly from the gauge fixed Lagrangian, and that is because there is a gauge symmetry. And if you want to kill this gauge symmetry, you impose the gauge. It means that you impose one more constraint, but that you do by hand in order to kill the gauge symmetry. So from this point of view, you can say that you have two constraints: Coulomb gauge plus Gauss law. Maybe this is what was that. If you want to consider electrodynamics and write down, say, for instance, the propagators for this theory when you quantize, then you cannot live without imposition of the gauge. So another gauge condition, so not another gauge condition, but just you need one more constraint, which you can call Coulomb gauge, or another gauge.
So the two constraints were the divergence of the moment. So yes, the divergence of the momentum and the zeroth component of the momentum.
Zero component of the momentum is there. Okay, so
we kind of forgot about it.
Yes, there is this primary constraint. It's a primary constraint. D0 P0 is equal to 0. This is a primary constraint. But this constraint, how to say? I mean, for our gauge fixed, for our Lagrangian, phase space Lagrangian, in a way, it simply tells us that A0 comes into Lagrangian without its derivative. Because P0 equals 0 simply means that A0 dot is absent. So now it depends how you look at this, I mean, how you count this constraint. So from the point of view of gauge fixed Lagrangian, which I'm writing here, I actually don't see this P0 equals 0 because simply it's a statement that in this Lagrangian, you don't have A0 dot, which is a direct consequence of the fact that A0 dot is absent in F menu. I mean, yes, if you start from the very beginning, yes, then you find this P0 equals to 0 as a primary constraint. And TIPI, it's simply Gauss law. But from the point of view of Hamiltonian dynamics and from the point of view of this Lagrangian, there is only one constraint, and this is what I'm saying, DIEI is equal to 0, while A0 plays the role of Lagrangian multiplier.
This is also strange because we have written down the generalized Hamiltonian, and
yes,
this generalized Hamiltonian contains two additional terms. So the one what they called the symplectic structure.
No, symplectic structure has nothing to do with the Hamiltonian. This is just something which tells you what Poisson bracket is.
Oh, no, yeah, you're right. So there were two additional terms. One was one of these terms was
Hamiltonian.
Yes, for the like the same we have here with A0, but with arbitrary function. So Lagrangian multiplier instead of A0. And another was with another Lagrange multiplier and P0.
No, that term I'm not sure I have to add here. I simply do not see why is the need for that. You mean one more term?
The Dirac procedure calls for it.
Not necessarily. I think the Dirac procedure at the end is equivalent to what I'm saying here. You don't need it. I mean, I just write the phase space Lagrangian, and I'm saying very simple thing. Phase space Lagrangian should start from the symplectic structure, and then the rest. And the rest, whatever it comes from the original Lagrangian. And I just compute the rest, and this is what it is. So from this point of view, my statement is that the fact that P0 is equal to 0 is simply a statement that my Lagrangian does not involve A0 dot, okay? And if it does not involve A0 dot, this tells me that A0 is a Lagrangian multiplier because it comes without time derivative. And its multiplier to the constraint DIEI is equal to 0. That's it. What I would like to say is that with this Lagrangian, I completely reproduce the content of Maxwell equations. I reproduce Maxwell equations. That is all what I need to have, right? Reproduction of the original equations. I see that Lagrangian, which I'm discussing, gives me exactly what I want. So Hamiltonian generates Maxwell equations, and it also, this gauge fixed section also generates the constraint divergence of E is equal to 0. No, and H is by definition is a curl of A. So all content of Maxwell equations sits in this Lagrangian. So once again, it depends. You see, sometimes it's possible how to say, yeah, I know what you mean, of course. It's possible to extend the Lagrangian a la Dirac, and indeed take into account all constraints, including primary constraint P0 is equal to 0. That is possible, I agree. There is the Dirac procedure which allows you to do this. But somehow you can consider a reduced version of this, where I effectively already accounted this constraint P0 is equal to 0. So I'm a little bit already reducing, how to say, all this Dirac procedure. Again, by simply saying that P0 is equal to 0, all what it gives me, what it tells me is that A0 is just a Lagrangian multiplier. Okay?
Yeah.
In principle, Dirac procedure is telling to consider the Hamiltonian as canonical Hamiltonian, which is computed by the standard formula PQ dot minus L. Plus, in addition, you should take into account the you should add constraints multiplied by some Lagrangian multipliers. All constraints which you have multiply with the Lagrangian multipliers. That is possible, but the Lagrangian multiplier for P0 is actually P0 on the constrained surface is equal to 0. So when I will be fixing the gauge, I have to solve the equation for P0, but it's 0, and therefore this term will decouple automatically. I will not see it in the in the Lagrangian at the end. And that is what I see. It's kind of a little bit reduced version of the Dirac procedure, if you wish. Okay. Okay. So let's see. What I want to do now is to construct the expansion of the field AI into a transverse path and a longitudinal path. And I want to do the same with the field EI. I will say that it contains transverse path and the longitudinal path, like this. Or in more detail, I can say that this is AI. It contains AI transverse, which is divergentless, plus a gradient of some function psi. And the same is here. I can say that it's divergentless path plus a gradient of some function zeta. Now, for this divergentless path, we know that it's by definition satisfies the equation that divergence of AI transverse is equal to 0. And the same, of course, is here. Di EI transverse is equal to 0. Now, this decomposition can be constructed in the formal way as follows. So Di AI, because of this transversality, is simply nabla squared, which is Laplacian acting on zeta. And the same, and from here it follows that zeta is given by the inverse of nabla squared applied to djaj. Let's write it in this way. So I'm inverting a Laplace operator. I'm inverting in the Laplace operator. That means that I'm applying inversion of the Laplace operator. It simply means that it's a Green's function, right? It's a Green's function acting on dj aj. And so AI transverse then is given by AI minus AI transverse is AI minus di zeta. But zeta is given by this formula, and so you see it's AI minus di dj divided by the inverse Laplacian acting on aj, which can be written in the following way. This is delta ij minus di dj inverse Laplacian, all this acting on aj. This is how transversal path is constructed. In particular, we see that we can introduce an operator Pij perpendicular or Pij transverse given by delta ij minus di dj divided by nabla squared, which is Laplacian. And this operator has the following property: Pik transverse, Pkj transverse is given by delta ik minus di dk nabla squared, delta kj minus dk dj nabla squared. And let's open the brackets here. Here is plus. Oh, better not to write anything. If we open the brackets, so what we get? Delta by delta gives delta ij. Then there is minus delta I delta j divided by nabla squared minus delta I delta j nabla squared plus delta I delta j, and then delta k sum over k gives nabla squared. So one nabla squared cancel, and then you get nabla squared. Then this canceled, and you get delta ij minus di dj divided by nabla squared, which is again Pij transverse. So in a way, this means that this operator P transverse is simply a projector. It satisfies the projectorial property. P squared is equal to P, if you wish. So it's a projector. So this operator is a projector. So it projects on the transversal path, on the transverse path of the field A mu. But it's a non-local operator because it contains the Green's function. This nabla inverse nabla squared is a Green's function. Now it's interesting that the field A is that the field H depends only on the transverse degrees of freedom. It does not contain longitudinal contribution of the longitudinal path, because H, let me write HI component, is given by minus epsilon I KL. I've written down before this expression via FKL, but FKL, if you write it down explicitly, and that was minus 1/2, but if you write it via the potential, then this is dkAL. This is how it looks like. HI is epsilon minus epsilon IKL dkAL. And now if we substitute here the decomposition of this field AL, then this is minus epsilon IKL dkAL transverse minus epsilon IKL dk dl zeta, dk dl zeta. But then you see, since it's antisymmetric in indices k and l, and derivatives dk dl commute between themselves, so the order is not, the order can be changed, then this is simply 0. So longitudinal path of the field A mu, or the field AI, does not enter into magnetic field. So magnetic field depends only on the transverse degrees of freedom. That's an interesting observation. So is it now clear how this Helmholtz decomposition is constructed?
Yes.
This is by using this projector operator. So this is a way how you can split, how you can separately find longitudinal and transverse part of the field mu. Now, let's talk about what happened if you include the sources. No, sorry. Let me first finish the case without sources. The sources we will still have to come. What I promised is to show how gauge fixed Lagrangian looks like if you separate transverse degrees of freedom from longitudinal degrees of freedom, because then it becomes completely clear what are these unphysical degrees of freedom which you would like to eliminate and how you can eliminate them. So gauge fixed Lagrangian. Once again, we start from the Lagrangian, which has this form: -1/c integral dx ei ai dot -1/2 dx ei squared plus h I squared plus integral dx a0 di ei. And now I substitute this decomposition of the field AI and EI in terms of longitudinal and transverse path. And so L becomes, in this case, let's see, -1/c integral dx ei transverse plus di zeta a dot I upper index, sorry. And so I need now to accommodate both index I and the definition of transverse. So let's write I transverse plus di zeta dot. Yes, so transverse part plus longitudinal part of A dot minus 1/2 integral dx. Here ei is ei transverse plus di zeta squared. With magnetic field, nothing happened because it depends only on transverse degrees of freedom, so I'm not touching it at all. So it does not have longitudinal contributions. Plus dx a0, and then di ei, it does not contain transverse part because of this derivative di. So it contains only longitudinal part. So ei contributes longitudinal part as di at zeta. And so di zeta gives exactly the nabla squared acting on zeta. So now what we can do, we can integrate by parts and use the transversality condition. For instance, when we integrate here by parts and put derivative on ai dot, because it's transversal part, this di will eliminate this. And another way around, so this di integrated by parts, it will act on this ei transverse, it will eliminate this term. So number of terms will be eliminated because of integrating by parts and transversality condition. And so, for instance, from this symplectic part, instead of 4 terms, when you open the brackets, there will be only 2 terms left. And so this will become -1/c integral dx ei transverse e dot I transverse plus nabla squared zeta multiplied by xi dot. multiplied by xi dot minus 1/2 integral dx ei transverse squared minus zeta nabla squared zeta plus hi squared. That is coming from the Hamiltonian. And finally, there is also this term with the Lagrangian multiplier, which delivers nabla squared zeta. So this is what is written down here. This is nothing else but the original Lagrangian of the theory, and it's invariant. It remains to be invariant under gauge transformations. So what is interesting to see here is the following, that first of all, you have transverse degrees of freedom. They are given by AI transverse, EI transverse. And so these degrees of freedom are conjugate in a sense of the Poisson bracket. Yes, that's because of this symplectic structure here. But also what is interesting is that longitudinal path coming out from the field A mu conjugate to the longitudinal path, essentially to the longitudinal path of the Gauss law, of the constraint. So longitudinal path of A mu is conjugate to longitudinal path, acted a bit with this nabla squared of our constraint. So in a way, constraint appears to be conjugate to longitudinal path, so unphysical path of the gauge potential. Right? That's because that's what we are reading off from this symplectic path of the Lagrangian. Now, so we have a pair of canonical variables. So in other words, they are canonical variables. So when we do, and this is clear separation now on physical degrees of freedom, which are sitting in this transverse path, and the longitudinal, that is unphysical degrees of freedom, which are encoded in these functions zeta and zeta and how you call it, xi. So this is xi and this is zeta. Now, when we impose divergence of E is equal to 0, divergence of E is equal to 0, this is the same as nabla squared zeta is equal to 0. This is Gauss law, which is constraint. And when we say, when we impose divergence of A is equal to 0, then this is equivalent to saying this C is equal to 0, and this is imposition of the Coulomb gauge. Yeah.
You said earlier that the representation by which the four potential changes is reducible. Could you please clarify what is the invariant subspace with respect to which makes this representation reducible, and what is the physical meaning of this invariant of existence of this invariant subspace? Like, can we in the terms of these longitudinal and transversal components, can we describe this invariant subspace?
I think invariant subspace is essentially the one which is given this AI perpendicular or AI transverse path of our field. This is what it is. But the point is that in order to extract it, you need a non-local operation. You cannot do it locally. There is no way you can.
Oh yeah. Could you please explain this in a bit of detail?
No, I don't know which kind of detail you want. In principle, one has to look at exactly how Poincare group acts on A mu, in particular on this AI transverse, and show that in fact this is a kind of invariant subspace. But again, the point that you cannot take it locally, you cannot extract it locally, that is precisely what is related to this fact that it is indecomposable. So you cannot do it locally. I mean, this procedure which you see here is involving inverse Laplacian, which means Green's function, and which means that this is non-local operation.
So, like the mathematical meaning of this representation being reducible but not completely reducible is that we can choose a basis in which there is a block which does not.
There is a block. Yes, there is a block. Indeed.
Yes, but beside this block, there is also a non-zero three vector.
Yes.
And I would like to understand the physical meaning of this block and like these non-zero components of the this three vector.
Yes, it's possible to understand, but it requires, I mean, it requires a little bit of investigation. So I'm not sure that at this point I can do detail, I can make details of this. So in principle, it's something which should be worked out. So I'm giving you a statement, but I'm not giving you a proof.
Okay, understood.
Okay, so in principle, I'm not sure that this is really good explained in the books. I'm thinking which book one could pick up to have a look. The point, of course, is similar in some sense to the infinite-dimensional representations of non-compact groups like SL2R or SL2C. Maybe looking in there, one can get an analogy, looking at representations of these groups which are infinite-dimensional and indecomposable. There are such representations. So in this case, they're a little bit similar to what happens to electromagnetic field, in a way. So this is probably the way to start looking at this problem, and this is block decomposition. The point is that you see what this procedure of detecting this transverse degrees of freedom, it breaks Lorentz invariance. Again, that's essential point of this consideration. By the way, the Poisson bracket, which you read of for transverse degrees of freedom, is also non-local. Now, from this symplectic structure, which is given by this AI perpendicular, or AI transverse, EI transverse, AI transverse, you read of the following Poisson bracket. You see that the Poisson bracket between EI transverse on X and AJ transverse on Y is given by -C And now I cannot write simply delta ij, delta function on the right-hand side, because that expression, if I write it like this, would not be compatible with the fact that on the left-hand side, we have transverse expressions. And so then on the right-hand side, what must appear is a projector of the original Poisson bracket on the transverse part. So di dj nabla squared delta x minus y. This is how the Poisson bracket between transverse components looks like. Now it is compatible with the fact that if I act, say, on EI by the derivative di I can take inside the Poisson bracket, it differentiates with respect to x. Then on the left-hand side, there will be di acting on this object, and then you see that it gives 0 because di delta ij gives me delta j. Then di gives nabla squared, so nabla squared cancelled, and I get minus dj acting on delta function, and this is 0. So this bracket is compatible with transversality. The same will be about aj. So if I act by derivative dj, then I also get 0 on the right-hand side. So this is a Poisson structure now for transverse degrees of freedom. That is what it is. So in other words, now everything is clear. Moreover, you see that funny enough, when you see on this Lagrangian, that in the free theory, it looks like you even don't need to impose the Coulomb gauge. Once you solve the Gauss constraint, when you say that nabla squared on zeta is equal to 0, then what happens is that you are killing this term. So this goes away together with psi. So there is no reason to put psi equals to 0. And this term also goes away, and this term goes away. And so this means that you are left with a Lagrangian which contains only transverse degrees of freedom, and even there is no need to impose the Coulomb gauge. Because
Only,
once you
only for the free field.
for a free theory, yes. For a free theory, this is, yeah, this is looks like this. But you see it from this Lagrangian. Because this mode, nabla squared zeta, interacts with psi only from this symplectic structure. There is a contribution of this longitudinal degrees of freedom of AI. And once you impose the Coulomb gauge, once you impose the Gauss law, then this longitudinal part goes away automatically. And you are left only with transverse degrees of freedom. And this is what you would like to call the gauge fixed Lagrangian. Gauge fixed Lagrangian. Only transverse degrees of freedom are present. Now, let's see what happened now in interacting theory. This is very interesting. So all what I need to account now, I need to account sources. So we come back to the discussion of gauge fixed Lagrangian, but this time without with sources. Now, in that case, we have to take into account the interaction term. And interaction term, what it contains A mu, G mu, like this. And this is, we can write as A0, J0 minus vector A with vector J. So basically, I put down the index I of J. Or other way around, I raise the index I of A mu, of AI. So I put it up, and then why there is this minus here. And this now I expand into transverse and longitudinal part. So field A I expand into transverse and longitudinal path, so it will give me a I perpendicular J minus nabla psi J. So minus gradient of psi multiplied by J. So Lagrangian, essentially, this is the same symplectic structure. Transverse path, longitudinal path, minus original Lagrangian. There's nothing happened to it. So it contains EI transverse squared minus this zeta nabla squared zeta plus HI squared. And now I start getting terms, I rearranging a bit the terms. So I have an interaction term to add. You remember I was adding to the original Lagrangian this integral a mu j mu dx. Yes, that was a term we have to add to account interaction with an external source. And now this a mu j mu I've written down in this way. So there are 3 extra terms. And now I rearrange them in a way that I collect terms containing a0, so Lagrangian multiplier. That was original nabla squared zeta, original Gauss law constraint. But now, in addition to it, I will get contribution from J0. It goes down there. And then there will be extra contributions coming from this term, which I integrate by parts. So this nabla goes to J, and it gives me minus 1 over C integral dx zeta nabla acting on J. And one more term containing the transverse path of A interacting with the current. 1 over C integral dx A transverse with J. Okay, so this is the full Lagrangian now with sources. If you vary this Lagrangian with respect to A0, then you get the Gauss law, which depends only on the transverse path of the electromagnetic field E. And now it contains the source. So this is the same as Maxwell equation with the sources. So divergence of E is equal to 4 pi rho, rho in Gauss system of units, where rho is a charge density. So J0 is just a charge density. And from here, actually, you can solve for zeta. So zeta now, since this is a equation with a source, you can solve for zeta in an explicit way. It is 1 over nabla squared, again, the Green's function applied to the source term, to J0C. And since we solve, in fact, algebraically for zeta, algebraically means that this equation, again, does not involve time derivative. There is no time derivative on zeta. In other words, what we have done, we solve the constraint, and the solution is given by this formula here. So zeta is given by this expression. We take this solution and substitute it back into our Lagrangian. So where does it come from? It appears here. Here we can just substitute nabla squared zeta. We can replace it by 1 over CG0, but then zeta itself comes in an explicit way here, right? So zeta, nabla squared zeta, we again can replace just by J0, but then we also have this zeta. And if I do that, then we will get the following Lagrangian. upon we solve the constraint. So minus 1 over c integral dx ei transverse ai dot transverse. Then we will get transverse part of the Hamiltonian. So it will contain ei transverse squared plus hi squared. Then from this term zeta nabla squared zeta, we will get the following non-local expression 1 over 2c integral dx g0 nabla squared minus 2, so inverse nabla squared, inverse Laplacian in other words, g0 plus 1 over c integral dx a perpendicular with j minus 1 over c integral dx psi nabla acting on j, so divergence of j, this is this term here, minus 1 over c j0 dot, and this comes from this term integrated by parts, and when integrating by parts there will be a total derivative, which is minus d over dt 1 over c squared integral dx psi multiplied by j0. I think that is complete expression which arises upon substituting in the Lagrangian solution of the constraint of the Gauss law constraint, but now with a source. What is interesting that here this term can be omitted, can be thrown away, because current is conserved. Current must be conserved, and this is also a consequence of the gauge invariance. I will explain it in a second. This, if you rewrite it in an explicit way by extracting the zero component, this is 1 over c g0 dot minus divergence of g is equal to 0. This is this has a different names. So this, first of all, this is a current conservation. And it's also called continuity equation in electrodynamics. And it comes from compatibility of the Maxwell equations. This is one way to see it. Because Maxwell equations in a covariant form has a following expression: d mu f mu nu is equal to j nu, where j nu is a current now, so it's equations with a source, Maxwell equations with a source. Now, if you differentiate it by d nu, you have d nu f mu nu, which is 0 because the stress, because the electromagnetic tensor is skew symmetric, and d nu commute, and so this is 0. But on the other hand, on the right hand side, you have d nu g nu is equal to 0. So current conservation is a necessary condition for the Maxwell equations to be compatible. Without this, Maxwell equations would not be compatible. So current must be conserved. This is also follows from the gauge invariance of this term, A mu J mu. Because if you do the gauge transformation, then this term acquires extra contribution like this. And if you integrate by parts, you will get chi T mu G mu. And since the action with an interaction term still must be gauge invariant if you want to achieve the gauge invariance, and you see here, this term explicitly depends on electromagnetic potential, not on fields E and H, but on electromagnetic potential. But if you still would like to have a gauge invariance, then this should be independent on chi for any chi, and this is only possible if d mu g mu is equal to 0 and the current must be conserved. And so with the current conservation at hand, what you get is that this term goes away. There is no this term. Total time derivative can be omitted as well. It also play no role because it's a boundary term. But because it's only a boundary term. In this case, you are left over with what? With the following expression. So essentially, you have the following thing. So you have Lagrangian, which looks like this. So the structure of the Lagrangian is like this. Transverse degrees of freedom, dx, EI transverse, AI dot transverse. So these are transverse degrees of freedom, minus Hamiltonian, minus 1 over C extra term describing interaction of the transverse degrees of freedom with the current. And the Hamiltonian this time, is an interesting object. So the Hamiltonian involves transverse degrees of freedom of electromagnetic field like it was before, dx EI transverse squared plus h squared, right? Plus additional term describing interaction of our currents G0. So this non-local term here. So if I now substitute the Green's function, so explicit expression for the inverse Laplacian, then I will get the following non-local term. So double integral 8p divided by c. So 8p appears, 4p appears because of the Green's function, dx dy G0 x G0 y divided by modulus of x minus y. So if you wish, the last term here, this term here, can be treated as perturbation of free electromagnetic waves. Free electromagnetic waves described by the by these terms here, by the transverse part of E squared plus H squared, transverse part of the electromagnetic energy. So perturbation of free electromagnetic waves. Okay, so electromagnetic degrees of freedom and their Poisson structure is still the same. So bracket between transverse AI and transverse EI is still the same. The only difference in the Hamiltonian is that now it contains this non-local term. And so this J0 is a zero component of the current, so it's a particle density. In fact, it's a density, particle density. And this term, if you think a little bit about it and remember our last discussion in the last lecture about the Coulomb interaction, you understand that this term is nothing else as a term which accounts for the energy of the Coulomb interaction. Energy.
Potential.
Yes, exactly. Potential, or since it enters the Hamiltonian, that's why I'm saying energy. You see, because it's a part of the Hamiltonian. Energy of Coulomb interaction. No, potential is an energy, yes. Potential, Coulomb potential. So it's very interesting. It's sort of even amusing to see that although we impose the Coulomb gauge, which effectively removes the scalar potential, so scalar potential is removed, because we know that in the Coulomb gauge, scalar potential is essentially A0, and A0 does not present anywhere. A0 goes, in fact, away. A0 was Lagrangian multiplier, but since now we solve for constraint, this term gets out of the Lagrangian, of the gauge fixed Lagrangian, so there is no A0 at all, no Coulomb potential, no A0. Nevertheless, Coulomb interaction did not disappear, but it's emerged as an additional correction to the Hamiltonian of transverse photons. So we have transverse photons, but on the top of that, we have the contribution coming as the energy of the Coulomb interaction. Now, you see, that's the reason why it is difficult to quantize electrodynamics. Coming now to quantum theory, I should say that this is exactly the difficulty with quantizing electrodynamics in the Coulomb gauge. Although this is a complete gauge choice, but if you start taking into account their sources, then this leads to a non-local theory, which is very difficult to deal with in a quantum theory. Because you see, it's really non-local. It's double integral, which is standing on the right-hand side here. And this is the reason why people, when they try to construct quantum theory, start to develop covariant approach to quantization of electromagnetic field. And we can talk about this a little bit later. Because to proceed with this Hamiltonian and quantum theory is possible, but very complicated because of the non-local nature of this perturbation. You can treat this term as a perturbation of free electromagnetic waves, but to proceed to higher orders of perturbation theory becomes pretty much non-trivial. Now, let me say something, start saying something about quantization. Let's assume that we are back to the theory without sources, and let's think that we continue to consider it in the Coulomb gauge. Then in principle, it's pretty straightforward to quantize the theory by replacing the Poisson bracket with a commutator. So quantization is in a way straightforward. So one should write EI transverse on X, AJ transverse on Y. This, instead of Poisson bracket, now I introduce a commutator, and as a result also there is H bar appearing, delta IJ minus DI DJ divided by nabla squared, delta X minus Y. This is how the Poisson bracket of the transverse degrees of freedom looks like. Now, transverse potentials can be expanded over plane waves as usual. And if you impose the commutation relations, like we are writing here, we can interpret, as in the Klein-Gordon theory, the expansion coefficients as creation and annihilation operators of transverse quanta. And an expansion over plane waves has the form, so you take a potential, transverse on X and T, it's a vector, and expansion looks like this. I write it with in all glory, with all the constants. So C divided by 2 pi in the power 3 over 2 integral dk, where k is the wave vector over which we integrate. Omega is the frequency, 1 to 2, two polarizations. epsilon r depending on k. I will tell you what is this. These are polarization vectors. And then I r on k, which will be annihilation operator, exponential minus I omega t plus I kx, plus creation operator, a dagger r on k, like this, exponential I omega t minus I kx. So two waves, again, just like in the case of a Klein-Gordon field. The only difference is that now we are dealing with the vector, and so we know that our photon or our electromagnetic wave contains two polarizations, and this is taken into account by this by this epsilon. And also for massless photon, we have k0 related. K0 is a zero component of the wave vector. It's as usual related to the frequency, so this is omega over c. And for massless photon, this is the same as modulus of k, because as you know, relation is k0 squared minus k squared is equal to 0 for photons. This is a dispersion relation for photon. Transversality condition is accounted by the fact that if I differentiate, if I take a divergence, so divergence means differentiation over x, and when I will be differentiating over x, k will go down. This wave vector k will go down, and then it will be paired. It will be, it comes as a scalar product of k with this three-dimensional vector epsilon, and so the condition is that epsilon r multiplied depending on k multiplied with k must be equal to 0. So r is taking values 1 and 2. So this means that I have two three-dimensional vectors, because A here is the vector potential, so it has three components. Vector potential, it has three components.
Could you please remind the definition of epsilon in this context?
Yes, I will write it in a second. So epsilon r is epsilon. So we have two vectors, epsilon 1 depending on k, and epsilon 2 depending on k. So two three-dimensional vectors, and these three two-dimensional vectors, they are orthogonal to the vector k. And so the situation is like this. We have the coordinate system built up from two vectors, epsilon 1, say, or epsilon 1, I'm putting here, epsilon 1, here, epsilon 2 here, and the vector k here, which is orthogonal to epsilon 1 and epsilon 2. So this is condition of orthogonality we require. And this condition of orthogonality to k, that guarantees transversality of the field A transverse. So the divergence of this is equal to 0. Now, so this guarantees that divergence of A transverse is equal to 0. And otherwise, it's convenient to choose these vectors to be orthogonal. So if you have now vector A that it lies in the plane orthogonal to k, this would be our A transverse, and A transverse decomposed over these two vectors, epsilon 1 and epsilon 2. And it is convenient, of course, to choose these vectors to be orthogonal as well. So that is why I'm writing them in this way. So they are orthogonal, and they are also normalized, so that if I take ER on K and multiply it, so take a scalar product with another vector, then the result of this is delta RS. So where these indices running values 1 and 2 are different, then you see orthogonality condition. And when it's the same index, then you see that the norm of this vector, norm squared of this vector, is equal to 1. These are called polarization vectors. These are called polarization vectors, so two vectors describing polarization of electromagnetic wave. Polarization.
Sorry, the formula that you have just written with the product of two polarization vectors being a delta
RS. Yes.
There is something strange with indices in this formula. You have plus minus in one, like plus minus on this, and RS on the right hand side.
Where you see plus minus, it's R here.
I'm sorry.
No, this is R and this is S and this is delta RS. Okay, so this is, conservation of indices should be present. Indices on the left-hand side should be indices on the right-hand side. Now, these vectors also satisfy what is called completeness condition. Completeness condition means that if you sum up, so here's 1 and 2, and you take epsilon R I on K, and you sum up with epsilon J R on K. So you are summing not the three-dimensional indices. So you're not taking scalar product, but you are summing over lower indices. So this index takes value just 1 and 2. Then on the right-hand side, you get delta Ij minus Ki Kj divided by modulus of K squared. So this condition follows from, it's called completeness. It follows from the fact that if you take an arbitrary vector in 3 dimensions, and you know that epsilon 1 and epsilon 2 and K form a basis, then you can expand any vector over this basis. And from this expansion, you can derive this formula, basically putting contribution of K to the right-hand side. Think a bit, it's an exercise to derive this. Derive this from the fact, again, that any vector in 3 dimensions can be uniquely expanded over epsilon y, epsilon 2, and k, which form an orthonormal basis in this space. So completeness condition. And if you wish, I can write down an explicit solution, a nice solution of this equations, of all these equations. For instance, you can take epsilon 1 on k, this 3-dimensional vector, to be the following: 0 minus k3 divided by square root of k2 squared plus k3 squared. And here you can take k2 divided by the same square root, k2 squared plus k3 squared. That's one solution for epsilon 1. For epsilon 2 on k, it's a little bit more complicated. It contains 1 over modulus of k in front. And here it contains square root of k2 squared plus k3 squared. Here minus k1 up k2 divided by square root again for this k2 squared plus k3 squared. And the third component minus k1 k3 square root of k2 squared plus k3 squared. So these are explicit realization of these polarization vectors as 3 vectors depending on components of momentum. And I chose these vectors in such a way that when you change k to minus k, so vector k, when vector k goes to minus k, then what happens is that the vector epsilon 1 reverse its orientation. So epsilon1 goes to minus epsilon1, while epsilon2 remains to be the same. It does not change its polarization, and so then the scalar product, say on k and on minus k, behaves itself in the following way. So it's -1 in the power r. Here is r, delta rs, delta rs. Okay, so what you can do further is you compute the electric field. Transverse path of electric field is simply given by -1/c.
I'm sorry. What is, if any, the physical meaning of these basis vectors?
These basis vectors represent two polarizations of electromagnetic wave or two polarizations of photons.
Yeah, but which two?
Epsilon1 and epsilon2. Photon has two polarizations.
No, I mean which polarizations? Because we have different types of, like, is one of them I don't know, are they two different circular polarizations?
No, this is not
is,
circular. No, this is not circular polarization. Circular polarization appears as a sum of two polarizations. So one polarization is a electromagnetic wave, is in the one, how to say, it's in the one plane. It goes in the one plane like this, and in the other it goes. It's two linear polarizations. Yeah, in the other it goes like this. So two linear polarizations. So this epsilon describes two linear polarizations. If you take a superposition of that, you can get other polarizations, like, for instance, the circular polarization, even elliptic polarization, and so on. But these are two basic polarizations out of which you can get, in a way, Lissajous figures by adding them up. Out of this, you can compute, of course, electric field. It's also transverse, and this is -1/c ai transverse dot. And this expansion, again, you obtain just by differentiating over time. So dk over 2 pi in the power 3/2 square root of omega over 2. That's what's coming from differentiating exponentials. Again, sum from 1 to 2. Polarization vectors, epsilon, depending on k. And then you have oscillators ark, epsilon minus I omega t plus kx, and plus, or minus, sorry, minus, because we differentiate over t, t comes with different signs. So r dega on k, exponential I omega t minus kx. And now, when you have this electric and if you have this potential, you know expansion for the potential. It's given by this formula. You know the expansion for electromagnetic field. What you can do, you can substitute this into commutation relations of the fields A and E, namely here. And you can detect from this expression the commutation relations for the commutation relations for the oscillators. Commutation relations for the oscillators. And these commutation relations for the oscillators have the following form. They are quite nice. So all what you detect out of these formulas will be the following. A S dega on K prime is equal to H bar delta RS delta function K minus K prime. So quite local, nice commutation relations, no non-locality. AR on K, AS on K prime is equal to AR dega, AI dega on K, AS dega on K prime is equal to 0. So essentially, canonical commutation relations for the oscillators, like we have seen before, for instance, for the case of the Klein-Gordon field, it's just that now indices R and S takes two values, 1 and 2, which correspond to two linear polarizations of our photons. And so A dega here are creation operators which create these polarizations. So I think my time is up, actually. You probably have another class coming. So what I will do next time, I will describe the physical quantity, which is called helicity of a photon. So I will introduce helicity. I will introduce the Feynman propagator. And then my idea is to talk a little bit about covariant quantization. Because as we discussed, if we have sources, then we have a problem actually with quantization because of this non-locality of the Hamiltonian. But for today, this is all. If you have questions, I am ready to answer.
I have a very small question about this.
Yeah.
Suppose we have two photons, two lights that cross each other. Do these two of different frequencies? So do these two photons interact with each other?
No. Photons do not directly interact.
Yes, because this is also confirmed from our commutation relation. mu should be 0.
Yeah, there is a deep reason. Two photons do not interact. You need more complicated thing to make them interact. But directly they do not interact. So in fact, it looks like, I mean, if you have just electromagnetic waves, just photons, then in principle, it's pretty much difficult to scatter light on light. There is such phenomenon, scattering of light on light, but it describes by higher order of perturbation theory. And so you need first to create electron-positron pairs, and these electrons and positrons must interact with another photon. So there is no direct coupling of photons with photons.
So do I understand it correctly that in the effective Lagrangian of quantum electrodynamics, there is an interaction term for
electrons with photons? That is, of course, yes. Electrons,
no,
positrons.
I know about electrons with photons, but photons with photons.
No, there is no such a term.
Even the effective Lagrangian for
yes, so
quantum electrodynamics is linear.
Yes, it is. It contains a standard Maxwell term F mu, but it's a free theory, right? So it's a free theory. It's a free electromagnetic waves. There is a Dirac term which describes electrons and positrons, and then there is an interaction term which couples a mu potential to the source term which is produced by electrons and positrons. So Lagrangian of quantum electrodynamics contains three terms: Dirac, Maxwell, plus interaction between Dirac and Maxwell. There is nothing else.
Yeah, because I have an acquaintance who tries to detect nonlinearity in electrodynamics, and from him I've heard that there are reasons to believe that electrodynamics should actually be nonlinear, but with
yes, of course, people investigate these effects, nonlinear electrodynamics. Yes, of course, there are such investigations. Sure, you can write more complicated actions, introducing high invariance, Lorentz invariance of F mu, and so on. Yes. So I'm talking about the standard, very well checked up to 5 loops, sort of Lagrangian of standard electrodynamics. Yes. then this is only contains, as I say, Dirac, Maxwell plus interaction of Dirac and Maxwell, nothing else. But nonlinear effects, yeah, people are trying to do this. There is action of nonlinear electrodynamics, which is kind of complicated. It contains a square root. So yes.
So for lights of very high frequency, so they might interact, right? Very high frequency.
Well, the interaction can run only through creation of electron-positron pairs, and then so basically you need to create electron-positron pair, a virtual one, and then another photon should somehow interact with, again, another photon should find this either electron or positron to interact. So it's a higher order effect, which is called scattering light on light. So there is such effect in electrodynamics, but it's of the higher order in perturbation theory. So it's a very rare event to happen. In fact, it describes in the books. If you open the, I don't know, for instance, even Bogolubov and Shirkov book, you will see that they describe it here, but it's a higher order of perturbation theory. So it's a rare effect,
but
of light on light.
If like, can we describe this effect on the classical level with some effective Lagrangian? In an effective Lagrangian which doesn't include an electron part, so the Dirac term.
No, I don't think it's possible. No, I don't think it's possible. I would say it's rather opposite what people try to do. They try to exclude the electromagnetic field from the Lagrangian by solving equations of motion for electromagnetic field. So in the old days, they have an idea that they can write something mechanical by excluding mediation. So basically, what does electromagnetic field? It mediates interaction. It mediates interaction between electrons and positrons. It's like, it's a massless field, it's a long range, and it's basically kind of connects electrons and positrons between themselves. So the idea is that in a way, one electron, say, produces, is source of electromagnetic field. It stands on the right-hand side of the Maxwell equation. It produces electromagnetic field. This electromagnetic field propagates, and another electron or positron gets into the media of this electromagnetic field produced by another electron. It interacts. And effectively, we say about interaction of electrons, but we know when we resolve it, that happens because there is an exchange by electromagnetic field. And in the old days, people thought that maybe we can just integrate out electromagnetic field from the Lagrangian, and we get an effective theory where we have only particles. It's like with the quantum mechanics of particles, no electromagnetic field at all. But of course, this idea failed because if you have particles and just mechanics, it's basically, you know, that in this case, when you look at such Lagrangian, then you get an idea that interaction must be instant, must have infinite speed. So because in mechanics, positions and coordinates of a particle are immediately determined by the coordinates and velocities of all other particles. So say Newton equations are supercausal in this case. You can say that in a sense that if something change with one particle, then other particles immediately know about this. That's like propagation is propagating, interaction propagates with a speed, with infinite speed. But we know, in fact, that this is not so, because there is a finite speed of light. The highest speed is possible, and signals propagate with this speed. So People try to do that. In particular, the grandson of Charles Darwin, it's also Darwin, tried to integrate out electromagnetic field, but then the resulting theory appears to be pathological. It leads to very strange things, like, for instance, free charge self-accelerates and so on. So very strange effects. So meaning that what you get is this effective action is quite unphysical. But integrating other way around fermions out of the theory, no one succeeded just to write down the action for a pure electromagnetic field. So both matter and fields, propagating fields, long-range propagating fields are both important.
Is there
In
a
principle,
book
you can construct effective theory. I'm not saying that this is not possible. You can construct effective theory by the procedure which we probably discussed. It has been invented by Coleman, but this procedure represents quantum theory as a classical theory, but with higher order terms. Yes, that's possible to do in principle. It's a way to recast the Feynman graphs, to collect the Feynman graphs, and if effectively what you do, you integrate out loops in this case, fermionic loops, or loops essentially, and you are left in a way with the blocks described by the tree-level graphs. But you have effective blocks which takes into account contribution of all these loops. And with these blocks, you construct a theory which in principle you can treat like a classical theory, but with higher order terms. That is what people did, and this is what is called Coleman effective action. Maybe we will talk about this later, indeed.